Well, welcome everyone. This is the CapEx IndustryCast. We're so excited that we have an opportunity today to talk to Mike Luehr from Dukane. He is the medical application specialist. If you recall, what we do here in IndustryCast is we go live every Wednesday at 11:30 a.m. We want to educate our customers about the technologies that we represent and work with out in our market, the North Carolina, South Carolina, and Virginia. And we want to just share manufacturing knowledge, any industry knowledge that we have picked up as it relates to manufacturing technologies. So we have people from Assembly Magazine on, we have people from different robotic companies, robotic grippers, actuators. So today, again, as I mentioned, we're excited to have Mike Luehr on. He is from Dukane, and he is our medical application specialist. So today he's going to be focusing on ultrasonic welding, so kind of an introduction to ultrasonic welding, and talk about some of the challenges that our medical customers face. But regardless of the fact whether you're a medical customer or not, if you are involved with ultrasonic welding, this will be an opportunity for you to learn from one of the best. Mike's been doing this for quite a while. So Mike, how many years have you been with Dukane?
14 years, but in the industry doing basically the same thing, about 34 years.
34 years of experience.
It's a long time.
Well, again, thanks for joining us
Sure.
here on IndustryCast, and we'll just be relying on your knowledge. You tell me when to flip the slides, and I will send them along. So.
Okay, great. Let's go to the next slide. And I'm just not trying to do like a big sales pitch, but just wanted to let you know that Dukane has been around for now 99 years. Wow. And so quite a few years, and obviously not doing ultrasonic welding, but started off with the first self-contained radio back in 1922. And then it kind of expanded from there and went into other things displayed at the World's Fair. I think it was in 1938, and then also helped with the war effort during World War II. And we also developed a film projector and quite a few electronic things. So
yeah, the very first, or one of the first transducers, right?
Yeah, we were in the early stages of development of that, and also the first system to weld by distance. And I'll explain a little bit later why that is important. But the first system to weld with a linear coder installed into it. And before it was just welding by time or by energy, and you had no idea how far the part was actually collapsing. So let's go to the next slide.
Yeah, for sure. Let's talk about collapsing. What does that mean?
Okay, so collapsing means that we are taking a part and welding it together. Now, before plastic welding came around, or people that don't really know that much about welding plastics through ultrasonics, when they think about welding, they think about metal welding, where a guy comes in with a stick and you see sparks all over and things like that. So this is nothing like that. What we're doing is we're taking an ultrasonic tool and basically compressing a plastic part. And then as we're compressing it, we're vibrating the parts together and creating heat through that vibration. So if you're rubbing your hands together very quickly, you can see that heat builds up in your hands. So if you apply pressure to that, eventually you get enough heat built up that you melt plastic, and that's what bonds the two plastic components together.
Yeah, and that's when we're talking the speed. Let's talk about the speed with which it's moving per second.
Yes, so the speed, there are different frequencies, and the main one that's sold around the world is 20 kilohertz. And basically what that means is that the horn or tool is vibrating at 20,000 times a second. Now it's on a microscopic level, so you don't actually see it, but if you lightly touch it, you can actually feel the vibration of the horn expanding and contracting. And it does that 20,000 times a second. We have
Wow.
other frequencies, and that goes up to 40 kilohertz, 30 kilohertz, 35 kilohertz, 70, 50. We go down to 15 kilohertz, which is not really ultrasonic vibrations because it's within the hearing range, but it's still vibrating plastic components together.
So and that's that reciprocating. It's doing this, but it's doing it. Well, it's actually doing this, right? So it's, but
Yeah,
it's, the one part is stationary or fixed, and so
right.
20,000 ups and downs per second.
Expansions, yes,
That
yes.
is
And there's a video
amazing.
clip, I think a couple slides down. So basically this horn, which is the silver part on top, is going to come down and apply pressure on top of the plastic component, and you will see that it will vibrate the parts together. And it's a very quick process, very clean process. Right now, I think that cycle time was maybe 250 milliseconds on actual time. And you can see how the horn comes down. We call that a sonotrode or a horn. It comes down on top of the part, applies pressure, and then starts vibrating at 20,000 times a second.
Now, how does the amount of pressure that you're applying during the welding process affect the weld itself?
The more pressure that you apply to the part, the more you travel in your collapse mode. So
Okay.
in other words, if you have something that's set at a force of, let's say, 10 pounds, and you turn on the sonics, it's only going to collapse a certain amount. Whereas if you have a force of maybe 100 pounds, it's going to collapse much further during that same time frame because you have a lot more force applied as the parts are melting together.
So would you want more force, less force, or just depends on the collapse distance you want? How do you determine that pressure?
Yeah, so good question. It is dependent on the size of the part, the type of weld joint that we designed in there, and then also the wall thickness. And the reason why the wall thickness is important is because if the wall is too thin and you put too much force on there, you could already pre-collapse the part, not at the weld joint area, but the part sides could be bowing in a little bit or
Yeah.
vibrating too much. So force is dependent on what we can determine as getting a good cycle rate, a good speed, but not collapsing the walls by having too much force on it.
Now, polycarbonate, that's what we're welding here
Yes.
in this video. That's
Hmm.
a very common medical
Correct.
plastic, correct?
Correct. Correct. And that's why I used it. We also use Eastman Triton is getting more popular in the medical field. Some disposables also are made of polypropylenes. Those are more difficult to weld because of the type of material and the fact that it's a little bit more pliable, but it also can be welded.
Now, the polycarbonate can be a challenge as well, because it's so hard, correct?
Yeah, we can
Or
balance
brittle.
it. We can balance it. It's not too brittle, but sometimes if the parts are clear, uh, which a lot of medical customers do have clear parts, you could see a frothing or a bubbling of the material that shows up in the weld joint.
Mm,
So what we have to do is kind of compensate with adjusting the amplitude or how much time we're spending on top of the part so as not to boil the plastic, basically.
I see.
This one is showing the ultrasonic process in general. So basically, we fixture the parts, we come down with the horn, we vibrate and collapse. The horn is doing its vibration there. Then we have a hold time, which allows the material to solidify under pressure. The reason we need to do that is if you withdraw the horn too quickly, the part has some memory to it and it could expand to the point where the material microscopically could stretch apart and cause cavitation. So we want to let the material solidify underneath a pressure. And then of course the last photo was or portion was the horn retracting where you can remove the part.
Sure. So let's talk now. What is this little point called here?
So that's the energy director. So basically what we need to do is have a energy concentrator designed into the part that will melt or initiate the melt much more easily than if it was just flat to flat.
Got it.
And further on, I have some slides and some examples. But
Sure.
basically what we're trying to do is if you weld a part flat to flat, you have a much larger or wider area that you're trying to heat up and bond together. And that could actually require us to have too much time applied to the part or too much energy where you would have basically product damage. So what we need to do is have some kind of energy concentrator to help initiate the melt a little bit easier.
Mm-hmm.
And from there, uh, we get a good solid bond. We just have to make sure it's designed properly for the material and for the wall thicknesses that the customer has.
Gotcha. So in this, when we're, am I correct in my understanding that the weld joint is actually stronger than the individual part after it's welded?
Yes,
If it's done properly.
in some cases and some parts, it depends on the material. So
Okay.
what we found is that with certain designs, we can get a weld joint as long as the material is encapsulated at the weld area, which I can show you later. That forms a great hermetic seal and a good bond. And when we pull test the parts, the wall of the part could break before the weld joint does.
Yeah, and so that's
Mhm.
that testing process is what we would do to verify that we've got a good joint, right? So
Correct.
we've got that in our lab, right? So that's another thing for people to know is
Mhm.
Dukane has multiple labs kind of around the world,
Mhm.
and
Yes.
so wherever you are, there's a lab probably not too far from you where you can send some parts and we could do some
Mhm.
initial
Yeah.
welding and verification that it's
Right.
fine.
We have labs in throughout Europe, China, Japan, Mexico, quite a few here in the United States.
Mm.
So we have pull testers, and then sometimes the customer needs to pressure test it, their parts for leaks, and from there we can either come up with something, or the customers will send their test equipment to us, and then we'll just when they come in for their FAT, uh, use their equipment to pressure test the parts.
Yeah, yeah, very common, right? That's
Correct. Correct.
that's one of the reasons why we sell leak test equipment or work with
Yeah,
somebody
exactly.
who does leak test equipment is what gets welded typically gets leak tested.
Right. Exactly. Especially if it's like small filters and things like that.
Well, tell us about this stack we've got pulled up here.
Okay, great. So this slide is showing a basic ultrasonic stack. So for those of you that don't know ultrasonic welding, basically we're taking an electrical signal into our generator. A generator changes that signal to a different to a frequency and brings it to the transducer. So the transducer has ceramics on the inside. So the electrical signal excites those ceramics in there, so they start vibrating, and they're tuned and developed in such a way that they will expand and contract. And that transducer then is connected to the booster or amplifier, and that booster will amplify it will either increase or decrease the signal that comes from the transducer. Then that signal is transferred to the horn or sonotrode, and that will expand and contract and bring that vibration to the part, sort of like the video was showing.
So this area here is kind of the neutral point, center point. Is that
Correct.
correct?
That's the nodal area, and that's where the booster is mounted. So it's mounted there, so it's rigidly, doesn't move around during welding, and that way it just goes in a Z axis.
Yes, that allows us to grip onto it.
Yes, correct. Correct. That's one of the mounting points. The other mounting point would be around the transducer housing, and that is isolated from vibrations also. So you basically have 2 points that we use for mounting.
Makes sense.
Okay,
Hey,
and
there
that's
it is.
a live picture of it. And basically this one is we're clamping around the booster ring. Like we were saying, it's isolated. The horn or sonotrode is on the left side. The transducer with the ceramics internally are on the right side there.
Yeah, what is that? What fitting is that? Is
That's
that for air?
a air cooling fitting. So sometimes when we're doing high-speed automation, or this one I think is would eventually be set up for doing maybe food cutting or food processing. So we have air going into there to kind of dissipate the heat that the ceramics could be developing from doing 24/7 welding or cutting.
Yeah. So again, everyone, this is the transducer, this
Mhm.
is the booster, and this is the horn or
Right.
sonotrode.
And there's just a stand that's clamped on the booster. So that's not in the typical welder system, but this is run as a probe system, which
Yeah.
means that the stack is outside the press and is put onto some type of automation that will weld
Yeah.
the
So it's
parts or
probably
cut food.
attached to some cylinder that's going to move it
Hmm.
up and down.
Correct, correct. Hmm. Yep. So this here just kind of shows the vibration of a tooling stack. And you could see where the colors are red is where we have the highest amount of motion and of stress. Now, this is exaggerated just to show us
Sure.
as we're developing this, how the welding is taking place. You can't really see the motion on this, but I thought this was kind of interesting to show people that don't understand the vibration, expansion, and contraction process, um, you know, what this would look like exaggerated.
I still think it's amazing that if I say the engineers that do this all the time, it just they they know instinctively what to do as far as the different ratios and
Correct.
booster and horn designs.
Correct. Oh, I was just going to say on that last one, where it's green, you could see that that's where the least amount of stress is. So that's where the mounting point is on the booster and on the transducer. And then towards the left, in the middle of the horn is a nodal area also. So that's where the least amount of stress is on the tooling stack. So basically on three pieces, you got three pieces of um, almost zero stress points.
Got it.
Okay. So, and that's once again the close-up of the weld. Yeah, sometimes it's a noisy process if we're doing glass-filled nylon material. And here we see various horn sizes. And
Yeah.
basically what we're doing here is we're just showing different frequencies that we weld in. As the frequency changes, the horn size changes. So basically when a customer sends us a part, we look at the size of the part and then the material. And from there, we determine what is the best frequency for that particular project. So here we could see 20 kilohertz, 30. So the frequencies, as they go higher, the tooling gets smaller. And then to the left is the 15 kilohertz. And generally that requires a sound enclosure, just because it is kind of a noisy process.
Yeah, those are hogs there.
Yeah, for sure, for sure. But they could do large parts.
Right.
So, and then here's just some typical tooling that is made. On the left, there's a urethane that's cast to the parts. And we use that a lot to prevent marking, or if the parts are severely, not severely, but extremely contoured, like a staple handle or surgical uh, knife or something like that. And then to the right is just another type of tool that we made for an automotive customer. So there's the horn. It's much larger than what we saw previously. So it's a rectangular horn with slots in it. And then the fixture below it is raised up because that part will eventually have some wires hanging out of it that we couldn't crush or didn't want to crush.
Got it. Sure.
This here is just what we would call some energy concentrators or ultrasonic weld joints. So to the left, we have a round design, which we usually recommend when our customers are using our servo ultrasonic welders. And basically the nice thing about that design is it's easier to manufacture. It's easy to fill out when molding, so it's very consistent in molding that part and for welding too. The middle one is a shear joint, and that is basically we're taking a wall and shearing it down, and that's used for application that's needs high pressure or high weld strength for welding. And then the one on the right is a tongue and groove, and that one has a sharp energy director. But basically what we're trying to do is get that energy director that has the E on it to fill up the groove once it starts melting. And basically, then you have a U-shaped channel of melted material. So then you have the walls, in addition to the melt material, to give you that strong hermetic seal.
So the welding in this application is here,
Correct.
and not here.
Correct. Yeah, where the E is that energy director, which is probably 90 degrees, will do the melting, and then we'll just weld to the bottom of that. So basically we're welding A, the letter A. So that's the distance that we're actually welding.
Makes a lot of sense.
Okay. This here is a close-up of a section view of the weld. So basically this one is, I think 690 microns. Our pictures are covered. Yeah, 690 microns.
Yeah.
And basically we're just showing what the energy director looks like once it's melted. And you can see it's the width of the wall that's on there. And that creates a very strong melt. And in cases, even stronger than the wall of the part itself.
That's why we weld.
That's why we weld. Yes, correct. So to optimize a weld, we basically take the software that's in our equipment and we use the graphing capabilities to optimize the weld. And so it's not like you're just guessing, oh, let's try this parameter, that parameter. We generally give a customer a set of parameters that gets sent along with the equipment, and then they start off from there, and it should be optimized by the time the system gets sent to them. But if not, then we use the additional features of our software to help develop the process even further.
Sure. So this application here, so we've applied our pressure, and we have obviously moved into position.
Right.
So we're starting to weld. So things are starting to melt here. And then this is the collapse.
That's the whole, well, let me take a step back.
Okay.
So the blue is the distance. So basically where you see the timestamp, I think it says 062 or something like that. That's where the parts start to melt and the welder has given the go ahead to start collapsing. So basically we got two different types of systems. We have our pneumatically driven ultrasonic welders. And basically you're taking an air cylinder and using it to drive the collapse of the part. And the way that works is the horn comes down on top of the part. As soon as it feels some kind of resistance or trigger force, the horn starts vibrating and collapsing the part immediately. And that's what starts the melting process. However, we have developed a servo welder, which does things a little bit differently. So we come on top of the part, start vibrating, but we don't necessarily start collapsing right away until the material has softened, sort of like a pre-melt stage. And then once we get a certain amount of reduction in force, then the software says, okay, now you can start collapsing. And that's what this screen is showing. We have reached our melt detect stage in the welder saying, okay, now the material has softened. Now you can start collapsing. So you see the blue start to peak upward
Mm-hmm.
as you start collapsing. So where your arrow is actually at the end of the weld where we have our dynamic hold force. So basically that means that the sonics has turned off. We're going to start collapsing even further to kind of, pack the mold, so to speak. And then the last dot right above that is where you will have your static hold. And basically what that means is the horn is now stable. It's no longer vibrating on top of the part, and it's just stationary on top of the part to let the material solidify before the horn retracts back up to the home position.
Sure. And so the benefit of pneumatic, you don't control the speed and the force so much, right? I mean, you do with the force to some degree, but
Yes,
you don't control when that force is released during the weld process because it's always pressing on the part.
correct.
Where with
So, mhm,
the DC or the servo driven, we can control that speed infinitely, right? And so we can choose to
correct.
go faster, slower, or slow it down, or stop with the force altogether. And that's what we're showing here in
Correct,
this
exactly.
graph.
We're wanting to melt the plastic, and then we take the speed and optimize it to match the plastic. And that's actually where we came up the melt detect of the system. Is basically it detects the melt of the plastic, and now we start adjusting our speed or our force on top of the part to collapse at a certain rate that gives us the best strength
Yeah,
for that particular material and joint design.
it would get optimum uh, size, right? So we're more
Hmm.
precise in the end part, and we
Correct.
have a stronger weld at the end of the day because
Correct.
we're managing all of those. Um, it's interesting how it's gotten more and more. It just gets better and better and better over the course of time. I remember it was only pneumatic, and then we had wasn't it
Right.
two stage? We had two stage air
Pneumatics.
cylinder there
Hmm.
essentially.
Hmm.
Yeah.
Yeah. And right now we've developed the system back in 2009. And I would say probably 95% of our medical customers are purchasing the servo welders, mainly because of their consistency, the reliability, and it's easier to calibrate than a pneumatic cylinder. So definitely the servo is, uh, you know, proven by our customers that, they prefer that over a pneumatic system.
Well, if you're going to be in a clean room, also
Yes,
there's some benefits to having the
correct.
servo
Correct. You
application
don't
as
have to
well.
worry about bringing in air to the system. There's no air necessary. It's just basically you plug it into the wall and off you go.
Yeah, so you just essentially go. We went from kind of a you had to stand on one leg and hold your mouth right for the
Hmm.
the pneumatic stuff sometimes. I mean, and
Right,
then
right.
but I remember the saying was that Barton said that every time you set up a pneumatic welder, take some of the customer's parts, put them in a bag, label them, and throw them in your closet. And then when they call you up and say the welder's not working anymore, make sure to get those parts out and take them over to the customer whenever you're going to look at it, because inevitably it's the parts that have changed that are driving the change in the process.
Yes, yes. And we're even able to show that more with a servo because we're not, because it's always doing the same thing. So if something changes in the part or the process, we ask the customer, send us what you have for your weld program. We compare that to the original one when that was set up. And then we could see that they either changed the program or the welder is doing what it's supposed to be doing and their parts change. So it
Mm-hmm.
helps us troubleshoot with the customer much faster on what the issues are that came up.
One of the
Oh,
things that's always impressed
mhm,
me with Dukane in the years that we've been working together, the other principals that we work with are very customer focused, but I
mhm.
think Dukane is next level customer focus as far as how they serve their customers in the troubleshooting. Send me your probe, send me your stack,
Yeah,
send me your parts, send me what you got. We'll figure it out together, as opposed to saying, "Hey, it's all working," or it's not us, it's you. So
Yeah, it just helps
Yeah.
the troubleshooting. And one of the other things we found out with the servo is a reduction in particulate, because
Mm.
what happens is, and this could be electronic customers too, or anybody that's trying to eliminate or reduce particulate in their process. And basically what we found out is that since we have the melt detect feature turned on and we're softening the plastics before we're actually collapsing, we get a really big reduction, probably about 70% reduction in particulate generation during that process. Now,
Wow,
there's always going to
that's
be a little bit,
huge.
because basically we're taking vibrations and we're trying to generate heat. However, we can
Sure.
eliminate so much of it because we have the melt detect feature that softens the plastic before we do the
Right. Smash
collapsing.
it.
Yeah,
Mhm.
exactly. It's sort of like when we do uh, um, in vibration welding, where we preheat the plastic and then vibration weld it, because we're trying to reduce, eliminate particulate in a lot of lens applications that we're working with the automotive manufacturers.
Yeah, certainly. Yeah, Paul Cathcart was on
Hmm,
and
hmm.
shared his knowledge and Dukane's expertise
Yeah,
with
so we're
with
finding
that
more
as
and
well.
more in this clean welding technology that we're starting to focus on with IR welding and so forth, that particulate elimination, debris elimination can be done and controlled. You just need to have the right equipment for it.
Yeah, very cool.
Okay.
Yeah, and here's Melt Match. Here just talks a little bit about the latest welder.
Yeah, exactly. So basically what we're just showing here is that we come down when you get the signal to the press, we come down and apply pressure. We initiate the melt process, and then we collapse it in a controlled manner, especially with the servo. Then we have a hold process where the material solidifies and the horn returns home, and then we get data to our software, which the customer can use and store for later evaluation.
Excellent. So let me ask this question. So if you were to say the biggest challenge that over the last 34 years that you've learned
Mhm.
that customers face, what is that challenge and how do you work through resolving it, or how would you recommend that they work through resolving it?
Yeah, so I think the biggest challenge is when a customer comes to us after their part is designed.
Mm.
And if the mold is already made and the part is not designed correctly, or the best approach for ultrasonic welding, now we have to work with the customer and either try to make it work, or they have to go through extensive and expensive mold changes.
Mm.
So I would say the biggest, maybe one of the takeaways I would say from this is, get us involved as soon as possible in the process, in the design work, and let us help you in the design process before you go down the road and it becomes maybe even impossible to make changes or corrections to the mold.
Right. Excellent. That's great advice, and definitely have had that experience
Yeah, right.
with customers through the years. It's like, oh gosh, this is not designed for welding. I know you want to weld it,
Right.
but it's not designed for welding, because depending on the technology, you're going to make a different design, right? So if you're going to spin weld it, it's going to be
Correct.
a different design recommendation than if you're going to ultrasonic weld it.
Right. And there's a few parts where customers are expecting to ultrasonic welded, but because of the complexity of the part, we can't build an ultrasonic horn for that. So
Mm.
then we have to go to another process and redevelop it in that direction. The problem is sometimes the customer is either late or in a rush to get it out, and then that becomes a problem in switching technologies, basically. I mean, we could do it,
Absolutely.
but it's you know it's difficult to get it in a good time frame when we're behind the ball already.
Yeah. Well, this has been fun. I
Okay.
enjoyed it so much. Mike Luehr. So, Mike, how can people get a hold of you?
Yes, either through email, which is um, Luehr, so Luehr at Dukane.com, or they
Okay.
could call my phone desk here is 630-797-4913.
Wonderful. This has been fantastic. Again, my name
Okay,
is
great.
Russ Wells. This is the CapEx Industry Cast, and we will see you next week. Same time, same place.
Okay, appreciate it,
Thanks so
Russ.
much, Mike.
Okay, thank you.
See you.
Okay, bye.
Bye-bye.